All right, today we're going to talk about shear force diagrams as well as moment diagrams for beams and bending. And what we have shown here is a beam, and this beam is simply loaded at this point, and there are two reaction forces here and here, and we are ignoring the mass of the beam, and we are actually considering first what happens in terms of statics in order to find the force at B and the force at A. To do that, we construct a free body diagram, which is shown here. Free body diagram that shows this is the distance to A, this is B, or this is the distance which is L minus A. And when we do that, we can then construct a shear force diagram, something like this, which if we were to move this force to the center, we would have two equal-looking rectangles. Okay? Pretty classic solution. The question is, how do we plot that on mathcad? That's what we're going to do, is try and plot this segmented function so that it looks nice in mathcad, and that's what we'll see in the next screen. Okay, so what I've done is I've come along and I've defined L as being equal to 10 meters. You can of course change this at any time, and it'll just change the parameters. P is 500 newtons. A is equal to 6 meters. And I can write this function, v of x, with an if statement. And an if statement allows us to define for x less than a certain value, otherwise it's this value. Now, because we're going to be doing some more complicated examples later, it turns out it's a lot easier to use the programming tool, and you can insert this particular type of if statement, which is actually entered by entering control quote symbol. If you do that and use the programming window and actually add lines, you can add as many segments as you'd like to add. So this does exactly the same thing. It has an if statement with an otherwise, just the same as this. What we've plotted is shown here, is plotted as v of x versus x, and I've defined the boundaries being from 0 to 10, and mathcad plots that straightforwardly, and I shaded this in here. I put some shading on this. That doesn't appear naturally in mathcad, but the red line actually defines the segmented function, and I also applied this grid here, which you can get to by double-clicking. Okay, so let's go to the next window, and we're going to find the value of the moment. The moment is simply the integral from 0 to x of the negative of the shear force, this v of x function. So straightforward, I just write m of x colon equals the negative of the integral from 0 to x, v of x dx. Since mathcad picks the numerical integration technique that it applies most appropriately, it picked the technique that it needed. And you can see from this particular solution, we get this slightly asymmetrical three-point bending situation with the maximum bending moment as shown right there. Okay, so very straightforward, very easy. Now we can use the same idea to do a little bit more complicated example. So we've taken this a little bit more complicated example, and what I've done is I've spread this same force, and I've spread it here across some distance, but it's centered at the same position A. Okay, so it's centered at the same position A, but I've actually distributed it and given a distributed force. In this case, this would be perhaps P divided by C per unit distance as we come along here. So for the free body diagram, we can just treat it as a localized force acting at the center, as is shown here. We get the reaction forces, as we've seen before, and the reaction forces are given here and given here. We can take that to the next step and define what happens with this spread, right? So we can actually look at that and think about, that must mean that we end up with a line going something like this. And as we'll see in the next case, that is exactly what I predict, something like that. And then let's go to mathcad and describe it. And in mathcad, here's the function we get. Okay, so pretty straightforward. Having gone through same distance, same applied load, same value in terms of the distance here, but I've spread this across 2 meters, and then I wrote v of 1, right, and for the positions greater than x plus c over 2, so for any position from here over, I've defined it as this value. and let me go back. I've defined it as this value. For the position in between, it's defined as P over C, and it acts when we're in between these two positions, A plus C over 2 to A minus C over 2. So it acts over this range. We get this particular function. It's whatever the magnitude is here, plus the gradient that comes along here, and then otherwise, it's this value, and it's the initial value. So this will be the value coming from the left. This value will give us the slope up, and this will give us the last segment coming along here, and this is what we see. Okay, so you can see it's the blue curve. It follows from here to here, from here to here, from here to here. Those are the three segments as defined for that gradient solution. So we can then take this, and it's plotted, you notice it's plotted versus the initial V, which was the concentrated force. We've now got the distributed force. And for this distributed force, we can also find the moment. We just take the moment as is shown here. This is this M1, and it's M1 of V1. It is going to numerically integrate it, going from 0 to x. And you notice that it deviates across those middle 2 meters, and it doesn't quite get up to the same magnitude of moment, right, because it's been distributed and spread across that range. Okay? So we have that distributed moment that comes across here. If we were to expand out and widen that force out, it would widen out further, and we'd be able to